To get started, we're actually going to define our system. So the system we're going to use will be so-called the closed fluid system. So it's going to be a closed system, and the material cannot be exchanged between your system and your surrounding. Fluid system means actually it can either be gas or liquid. So this is kind of the big umbrella you need to have in mind, because all our discussion will based on this. That means actually in the future, after you get familiar with all the concepts you have, you should be able to further extend these things to other systems. Another thing you're going to hear a lot is actually we're going to further simplify this fluid system into the simple system. So every time when we say the simple system, that means when we talk about the work, it's only the PV work. Eventually, things you're going to deal with will be the closed, fluid, simple system. So no material exchange between your system and surrounding, and in the work we talk about is only the PV work. So let's first discuss what is work. dW is defined as the force, capital F, times the distance that you travel. One thing special about work is actually it's directional. To calculate the proper work you do, you actually do the inner product. For example, if you do the things along the z directions, then these things can be further simplified as the force in the z direction times the displacement in the z direction, and that will be the work you actually done to the system. Okay, the work can be actually either your system done to the surrounding or the surrounding done to the system. So in different cases, you need to assign the work of the system. For thermodynamics, the things we care the most is the change of the system. The work is actually done onto your system, then you're going to have a positive sign. The sign matters a lot in thermodynamics. So you want to pay close attention that you know the sign of work to your system. Alright, so if today you have an infinite small amount of the distance moved, then we know the total work will be just the summation of your dW. It's actually the summation of force times displacement in the same direction. Second thing is actually for a closed fluid system. So here we are going to use gas as example. If you have piston, then outside you have your pressure P external. Inside you have your pressure of your system. To calculate work for this closed system, we know the work is going to equals to Fz times your ds in the z directions, right? We can actually rearrange these things a little bit. For example, I'm going to divide my Fz by the cross section of my piston. Okay, so the A is actually the cross sections of my piston. And then on the other side, I multiply A. So I didn't change the equation. So once I write the things, the first term is actually force over area. So this can be rewritten as pressure. What is the distance movement times your cross section? Volume, right? So you know this is actually dV. Since right now I actually exert the force onto the system, so should the work be positive or negative? Positive, right? The work needs to be positive because you're actually doing the work onto the system. But when you do this, how does it actually affect the volume of the gas? It's going to be a positive or negative value. Negative, right? Because eventually the volume becomes smaller, right? So you know pressure is always positive. Your dV is negative, therefore to match the sign, we need to put a negative sign in the front. So that the term on the right will be positive. Okay, so in other words, we can write the work is going to equals to negative P times or delta V. We write P here, right? There's actually multiple P in the things we just talked about. The first one is actually P external. You also have P system, right? Actually, there's actually an opposing P too. So what is the P we want to use? Is it P external or P system or the P opposing? Okay, it's kind of confusing, right? But right now, you can think about this. Who is actually doing the work? Your P external, right? You're actually doing the work onto your system. So the P here is actually P external. Very important, okay? This is actually the definition that you cannot mess up. Once you mess up, your sign won't be correct. Okay, so the work is going to define as negative times your P external dV. So this is actually a definition that you need to memorize. So, give you examples. If today, assuming your P external is 5 ATM, and initially your system have P system is 2 ATM. When you reach your final state, you know your P system is going to equal to 5, and then your P external is going to equal to 5 as well. So the work under these conditions is going to equals to negative 5 times delta V. And in this case, we know the final volume is actually smaller than your initial volume, right? So delta V is actually negative in this case. So this overall term is going to become positive. So delta V is Vf minus V initial of your system. The V is actually for your system. That's actually the first example I want to say. Okay, the second example is actually the opposite. Okay, if today your P system is 5, your P external is 2. Okay, so assuming that's your initial state. And then at the final state, you know, your P system is going to equal to your P external, right? So your P system is going to equal to 2, and your P external is also going to equal to 2. Okay, so under this case, we know dW or delta W to be more precise is going to equals to negative P external is actually 2 times your delta V. In this case, do you have a positive or negative delta V? Positive, right? Because the final volume is larger than your initial. Since this is positive with the negative sign in the front, you know the work will be overall negative. That means actually the system is doing work toward your surrounding. So your system is actually losing energy. That's why it's actually negative. Okay, so with this thing being said, okay, the next thing is actually how do we talk about the work of free expansion system? When we talk about the free expansion system, it's more like this. Still have a piston-like things, but right now it's actually on both sides are all closed. In between, you have a valve connecting the two chambers. On the left-hand side of the chamber, you have your gas. On the right-hand side is just vacuum. So once you have these conditions, then you open your valve. Then the gas can start to diffuse from the left to the right-hand side. So under this case, I want to calculate the work. Okay, because we know the work is actually negative P external delta V, right? When I say vacuum, what it really means actually your P external is equals to 0. So this is going to equal to 0 times delta V equals to 0. In other words, what it tells you is actually if a system is undergo a free expansion, what I really want to tell you is that the work is going to equals to 0. Okay, so the next thing we want to talk about is reversible work. So in your daily life, pretty much all the work you see is irreversible. But the reversible work is actually the one you can use thermodynamics to calculate it. For the reversible work, what it really means actually your PVT is always well defined. For example, previously we say your dW is actually equals to negative P external T times dV. When you have a reversible processes, okay, let's just use our piston as example. Let's say your P system is 2 atm. Your P external is 5 atm. Once you let the thing start to evolve, we will see the chamber is going to change its volume and then it reach its final state. Okay, and this happens in very short amount of time. In other words, that is actually irreversible processes. When you just let the things happen, it happens in an irreversible way. What it means is actually when these things happens, okay, along the way, before you actually reach the equilibrium, we have no clue about its pressure, volume, and temperature. Okay, and the reason is because once these things happens, let's say we have a really fast camera, we can capture all the things. So in the beginning, we know the gas should be randomly distributed inside your vessel. But once you let the things to evolve, because external pressure is so high, it's going to push your piston quickly. If you look at the time point that's before reaching the equilibrium, you're going to have a lot more dense gas molecules in the beginning side. In other words, inside your system, you don't have a homogeneous system. Since you don't have a homogeneous system, you cannot define the pressure of your system. The things we can define is actually after you reach equilibrium in the end, this becomes so dense, but it's dense homogeneously inside your container. Then we know your P system, again, is going to equal to 5 atm. What it means actually, you can define the PVT here, you can define the PVT here, but not somewhere in between. However, if today you have a reversible processes, then you can determine the pressure, volume, and temperature at any given point. Okay, so how do you reach the reversible process? The things you need to do is like this. Okay, here we say this is actually, you start from 5 atm, right? And then inside is 2 atm. This is not going to give you the reversible one. What you should do is actually, I start from 2.000001 atm. You just provide a very, very small perturbation that within your detection time, your system will already rebuild equilibrium. So under this case, you can still predict the pressure inside your system. Then you slowly or gradually increase the pressure all the way to this condition. Therefore, at any given time, you will always know the pressure. But the drawback is actually it takes forever. Okay, what's the benefit of doing that? Remember, this is actually how we define our work. If today you have a reversible process, you can actually swap your P external with your system P, okay, because they are always at equilibrium, right? They are going to always equal to each other. And I can use my P system to represent my P external. What's the good thing about this? The good thing about this is because if you have ideal gas, then you know you can write your P equals to RT over V dV. So once you do this, then you can actually integrate on both sides. Therefore, you know your work, which is actually going to be integral of your dW, is actually this summation, negative RT over V dV. Since we're actually under constant temperature, then these things can be RT, negative RT, natural log V2 over V1. So if today you have ideal gas, then you know you can go from your initial to the final state. If you can measure the volume change, then you can know what will be the work you can actually achieve.